Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss about draft tube theory and its efficiency. In our last lecture, we have already discussed about the draft tube concept, like how it is working and what is the function of draft tube. Along with that, also we have discussed about the application advantages and disadvantages of draft tube in our last lecture. So here we'll discuss about the draft tube theory and its efficiency. So to discuss about this one, I have considered a draft tube which is connected to a turbine outlet, but here turbine is not shown. So this diagram I have taken from the book. So this is our suppose turbine casing is there. Okay. So we know that the draft tube is used at the outlet of the turbine to maintain the pressure level, and because we know that at the outlet of the turbine we have a negative pressure head will be created, or we can say the low pressure head is raised at the outlet of the turbine, and to convert that high kinetic energy into the pressure, we used to use this draft tube at the end of the turbine. So that we have already discussed in the last lecture. So anyway, so this part will be our turbine part, and this is the, you can say, the turbine casing, and this is the outlet, exact outlet of the turbine, and from here we can say the draft tube is connected. So this is the structure of draft tube, what we have seen in the last lecture, the types of draft tube. So in that, suppose you can consider a conical type draft tube is considered here to understand the draft tube theory. So the draft tube is one end is connected to this outer end of the turbine, and outlet of the turbine we can say, and other end is connected to the inside the water level, and this is the water level, you can say the surface level of this water, or that is called tail race. This is called tail race, and this is the outlet of the draft tube which is inside the water, outlet of draft tube, and this is tail race, and this is the inlet of turbine, inlet of draft tube, and this is actually our draft tube. Okay, and here inside that, as I told you, that low pressure will be there at this point. So pressure is low, and here high velocity we have. Okay, high velocity is to there at this point. So due to that, we don't want to waste any kind of energy to the atmosphere, so that we are converting that velocity kinetic energy into pressure energy by the help of this draft tube. And at this point, you can see this is the surface level of water, as I told you. So here we have the atmospheric pressure, PA, we can consider here, and this is the water level. Yeah, and the distance of this, the inlet of draft tube we can give a section 1, and this is outlet of the section draft tube is given section 2. So the distance from this section 1, like from here to the tail race distance, is HS. So that is, we can say, the vertical height of draft tube above the tail race up to section 1. Similarly, this is why the distance from the bottom of draft tube from the tail race, like from bottom to here, the distance is y. So two things we have considered. One is HS, and which is nothing but, we can say, this is the vertical height above tail race, we can say, vertical height above tail race. Vertical height of, you can say, the draft tube, which is at the inlet condition, that is inlet point, we can also say. And the second one is y is given. Y is nothing but the distance, we can say, the distance from the distance of bottom tail race, or we can say the outlet of draft tube also, distance of bottom of draft tube from tail race, Okay, now what we'll do, as we know that there is a water is flowing through this from this turbine to the outlet of the draft tube, and that is existing to the atmospheric level. So you can say that inside the water level also. So there is a flow in the pipe. Okay, there is a flow in the pipe, though the pipe is slightly inclined, you can say conical structure is there. Anyway, pipe flow we can consider. So here we can apply the Bernoulli equation. So by applying the Bernoulli equation, we can write in the Bernoulli equation where you can apply section 1 and section 2. So apply the Bernoulli equation in section 1 and section 2, section 1 and we can write this is section 2. By applying this two section, what is our equation was there? We know that. So section 1, section 2, what is that? Inlet of draft tube, outlet of draft tube. In that we can write our equation. We know that P1 by rho g. This is P1 by rho g plus V1 square by 2g plus here Z1. We know that P1 square by P1 by rho g. This is what? P1 by rho g is nothing but this is, we can say this is pressure head. This is only P1 is the nothing but the pressure at the section 1. At this point, what is the pressure value is there? That is P1. And P1 by rho g is considered the pressure head. So that is at the inlet condition. Similarly, this is V1 square by 2g. This is our velocity head. So V1 is nothing but the velocity at the section 1 or at the inlet condition of the draft tube. Similarly, Z1 is the, we know that is potential head. Z1 is nothing but potential head is nothing but the distance from the datum line. So here let's consider the outlet of this point here, this one as the datum line. This is okay. This is our suppose datum line. So from here datum line to the inlet of the draft tube, how much distance is there? Okay, that is we can say datum head. That is pressure head, potential head or datum head also we can say. So this one we can write how much distance is there. We can see this is hs plus y, the total distance from here. So this one we can write datum head or we can say this is also potential head. Okay, because the total energy you can say that is pressure energy, kinetic energy and potential energy, that also we can say. Anyway, this is at section 1. Similarly, section 2, what we can write? The pressure head at the outlet condition, this is P2 by rho g. That means at this point, what is the pressure value is there and how much pressure is coming out and what is the head on this. So pressure head, that is actually, so that is specific weight. If you justify, we will get that one. Plus this is V2 square by 2g. Similarly, what is the velocity of at the outlet condition and what is the velocity head at that point. And similarly, what is the datum head or potential head at this point? So we have taken the datum line at this point. So there is no potential head or datum head or that because it started from here only, baseline. So that Z2 value here will consider this is 0. Actually, this one we can consider Z1 and this is our Z2. Okay. Similarly, we need to add one more terminology, that is what is the loss of head between this section 1 and section 2. So that one we can write in terms of HF, head loss. Head loss due to the friction between the section 1 and section 2, that we will write in terms of HF. The next one, so here we can mark it like HF equal to the loss of energy between here. Just I'll write one more terminology. HF is the loss of energy. We can say the loss of energy between 1 and 2. Okay. Now the next thing is the pressure P, like second pressure head, we can say the P2 by rho g. This one at this point, what we can write? So how much distance is there and what is the pressure at this point, at this tail race point, that means atmospheric pressure. So here we can write P2 by rho g. P2 by rho g equal to, we can write this is atmospheric pressure head, and the distance from this atmospheric pressure head to the datum line, that is nothing but y. So this one we can write like PA by rho g plus y. Okay. Now what I'll do, I will just put this equation in this value in this equation. So let's give this equation, suppose this is 1 and this equation we can just mark it equation 2. Put the value of P2 by rho g from equation 2 in the equation 1. So after substituting the value here, what will get here? P1 by rho g, first one, first equation. This is V1 square by 2G, and this is Hs plus Y, and this equal to, we can write this is on behalf of this, let's put the value here like Pa by rho G, and this is Y plus this is V2 square by 2G and plus HF. Now what I'll do, I need to find out what is the pressure head at this point, how much pressure is there and what is the pressure head at this point. So here this YY terminology, I just cancel it and I'll write here P1 by rho G. P1 by rho G is nothing but, I'll take this value here P1 Pa by rho G, Pa by rho G, and this Hs also I'll take it to this side, so that will be minus Pa by rho G minus Hs, and this minus I'll consider one terminology, that is V1 square if by 2G, if I take it to other side, so that will be minus, this is plus, so I'll take a common of minus here and directly I'll write the value like V1 square by 2G, V1 square by 2G minus V2 square by 2G minus HF. Okay, I have written directly by omitting one step here. If I will want to write one more step, then what I'll do, I'll take this value to the right hand side minus this value already there at this point, and this two terminology will be come to this side. So minus Hs I already have written, and V1 square by 2G I'll take it to this side and I'll make a minus of this. Suppose it will come here, minus will there. Then after that what will we do? We'll take a common of minus. Then this minus was plus here. V1 square by 2G will be converted to plus, and this will be minus, is plus is there, that will be minus, and this is plus also there, that will minus. So if I just to multiply minus into this term, then what I'll get, minus V1 square by 2G plus V2 square by 2G plus HF. That's it. So this is the equation of the pressure head at the inlet point. Okay, now here at this point, if you see this P1 by 2G, which will be always less than the atmospheric pressure head, because see the terminology what we are getting here, that should be, all these things will be minus from the this value. So obviously this is more, this pressure head will be more, that's why what value will get, that should be always less than the pressure head. That's why I used to tell here you will get low pressure or the pressure head is here less. This is the terminology. Now we'll see its efficiency. This is the theory of the draft tube, and now we'll see the efficiency part. So efficiency part, we know that we basically used to define the efficiency in terms of like output by input here. We know the formula, but the efficiency of the draft tube will be defined at the, this is the ratio of, you can say, the actual conversion of kinetic energy. You can write the actual conversion, of kinetic head into pressure head. This is output. Exactly how much kinetic head was converted from here. Kinetic head in the sense, what is the velocity I told you, kinetic energy, and what is the kinetic head was there at this point, and finally how much was converted here. So the actual conversion of kinetic head into pressure head, because we know that initially our pressure head was very low at this entry point. Now when it is coming to the outlet, it was increased. So how much exactly it is converted, that is our output. And what is the input? Input is nothing but kinetic head, exactly what is the kinetic head was there at the inlet point. So that one also I'll write here, kinetic head at inlet, of draft tube. So this is our efficiency. So here, yeah, what is the actual conversion of kinetic head into potential pressure head in the sense, this terminology actually, this terminology is considered as the actual conversion of head. But if you say only theoretical, I can consider only this part. Only how much theoretical conversion is there, V1 square by 2G minus V2 square by 2G. That is our actual, theoretical conversion of kinetic head into pressure head. Okay, this is the theoretical one. But if I say what is the exact one or actual one, actual means we need to consider the losses of energy. So for actual one, we need to consider the whole terminology here. And so what I'll write here, the equation, I can write this is V1 square by 2G minus this is V2 square by V2 square by 2G minus HF. This is our actual conversion of kinetic head into pressure head divided by what is the kinetic head at inlet head of the draft tube? That is nothing but at this point, what is the kinetic head? So already I told you previously, this is kinetic head is nothing but that is velocity head. Potential, okay, this one also we can write, this is kinetic head also. I have written velocity. Anyway, kinetic head also we can write here. That is kinetic energy, and in terms of kinetic energy, half mv square. In terms of that, we have written kinetic head, that was. So here we will write this is V1 square by 2G. This is our kinetic head at an inlet of the draft tube. At this point, what is the kinetic head? That is nothing but V1 square by 2G. As simple as that. In that, what is the term? What are the extra terminologies are there? Already I told you the terminology regarding the V1 and this is V2, okay, and HF. This HF already told previously. V1, V2 is nothing but the velocity of water at the inlet condition of draft tube. V2 is the nothing but same thing like velocity of water at the outlet of the draft tube. So this is about the efficiency. So I will write efficiency equal to efficiency of draft tube. Okay. This is our final equation. And here, this is our equation, draft tube theory. Okay. What is the pressure head at this point? At this point. So that is equal to pressure head, atmosphere pressure head minus this one. That's why I told you that always keep in mind at this point, what is the pressure head is there, that is always less than the atmosphere pressure head. So I hope you understand this theory, draft tube theory and efficiency. Still, if you are having any kind of doubt regarding this, you can give a comment on the comment box. Thank you all.